uses and widespread applications in physics, astronomy, technology, and even medicine. But to the scope of this video, we are going to limit ourselves to only 3 of those uses. Number 1, dimensional analysis can be used to find the unit of physical quantities. Yes, dimensional analysis can be used to do that. Okay, it can help you generate the unit of physical quantities. Number 2, dimensional analysis can be used to check the validity of an equation, or to check whether a given equation or mathematical statement involving physical quantity is true or not. Another way of saying this is to say that dimensional analysis can be used to check the validity or homogeneity or correctedness of an equation. Number 3, dimensional analysis can be used to derive an equation or the mathematical expression between 2 physical quantities. Now, these uses may sound really simple to you, but they are very powerful tools, as simple as they are. Okay, so in the next video, we are going to be looking at how we are going to apply these uses to actually solve problems. Okay, so we are going to be taking a few examples and solving questions to actually see how we can apply these uses like practically. So our very first use is that dimensional analysis can be used to derive units of physical quantities. Okay, let's demonstrate that. So over here, we are going to apply that use to find the units of these physical quantities. Actually, we've already done this. Example. We're actually applying dimensional analysis when we're doing those examples. We're finding the units of these physical quantities. We're finding the dimensions of these physical quantities. But here we are going to look at it differently. Alright, so how do I find the unit of density using dimensional analysis? What I have to do is to find its dimensions, and from its dimensions I can infer its units. It's as simple as that. For example, the dimensions of density will be the dimensions of mass over the dimensions of volume. So mass is what? The dimension of mass is m, volume is L cube. So from this, I can say that the unit of density is mass. What's the dimensions of mass, or the unit of mass for me? Dimension is kilogram. So I can say that it's kilogram over volume. L is meter cube. So kilogram per meter cube. Simple. It's quite an obvious application. Okay, so it's simple. Let's take another example. Force. How can I tell the unit of force using dimension? I first have to write out the dimensions of force. Then from its dimensions, I can infer its units. Okay, or I can deduce its unit. So force is given by mass times acceleration. And so the dimension of force will be the dimension of mass times the dimension of acceleration. So that will be mLt minus 2. And so therefore the unit of force will be kilogram for m, m for L, and then times seconds. So it's kilogram per square second. Simple. Okay, so you can try finding the dimensions, the unit of pressure in work using the dimensions, and you can put your answer in the comment section below. So because of how simple this is, you might think that, how useful is this? But it is very useful. For example, in a case where you are given a physical quantity that you've never seen before, that you're not familiar with, these ones we are all familiar with: density, pressure, work, and all. If I give you a physical quantity that you've never seen in your life before, okay, for the first time, how do you determine its unit? Okay, if you are given the dimension of that physical quantity, you can use that to find the unit. So in a case like that, it can prove useful. Now to our second use. Okay, so if you remember correctly, the second use is that dimensional analysis can be used to check the correctedness or the validity of a given equation. Let's demonstrate that. So I'm going to write some equations on the board. Okay, and hopefully you are familiar with those equations. Okay, so So, if you are familiar with this, you realize that these are Newton's equations of motion. Okay, these equations are actually correct, but we are going to check to see if they are correct. Okay, so assuming we don't know, Newton came up with these equations, and we don't know that they are correct. Okay, so what scientists are going to do is that they are going to have to sit down to check whether this equation is correct, because you just can't come up with anything at all. All right, so let's check and see if these equations are correct. But thankfully here we have a powerful tool, dimensional analysis, to check whether the equation is correct or not. Okay, so how do we do that? Okay, so let's take this example and let's demonstrate how we check for the correctness of an equation using dimensional analysis. All right, so number one, I'm checking to see whether this equation is correct using dimension. So the first thing I will do is I'm going to write, if this is dimensionally correct, then the dimensions of each side of the equation should be equal to the dimension of the other side of the equation. All the dimensions here should be equal to the dimensions here. If it's not equal, then the equation is not correct. That is the idea behind it. Alright, so what is the dimensions of velocity? Lt minus 1. This is also velocity, so Lt minus 1 plus Lt minus 2 times t. This will give us Lt minus 1 equals Lt minus 1 plus Lt minus 1 to the power negative 1. So this becomes Lt minus 1 equals, this plus this is 2, will give us 2 Lt minus 1. Since this number here is a dimensionless constant, meaning we can ignore it. We are looking at dimensions, not values that do not have dimensions, so we can ignore it. In other words, we can see that this does not exist in terms of dimensions. So this equation, this side of the equation is equal to what's the other side of the equation. So because of that, this equation is dimensionally correct. This formula is correct. Okay. So now let's try our second example. Number 2. B squared equals u squared plus 2as. Alright, so to check whether this equation is correct, the dimensions of the left-hand side of the equation must be equal to the dimensions of the right-hand side of the equation. So let's check that. B squared must be equal to dimensions of u squared plus 2 dimensions of a, dimensions of x. This will give me Lt minus 1 squared. Now notice that this is no more a square bracket, it's just now a normal bracket, because if I do this again, then it doesn't make sense, because how can I find the dimensions of a dimensions again? It doesn't make sense, because this is a symbol for finding the dimension of a physical quantity. So once I find the dimensions, I can't put them in square brackets anymore. Okay, so if I want to write anything, this is what I can do. Alright, I hope you get that. Okay, so dimensions of Lt minus 1 squared plus 2 Lt minus 2. Dimensions of s is L, not t, because this is not, remember this is displacement, not time or seconds, so it's L. So let me simplify this and see if I'll get, this will give me L2 minus 2. This will give me L squared t minus 2 plus 2 L squared t minus 2. So if I add this and this, because they are the same things, I'll get L squared t minus 2 equals 3L squared t minus 2. So if you ignore this, because it's a dimensionless constant, you can see in terms of dimension, the left hand side is equal to the right hand side. Therefore, once again, Newton is correct. Alright, so to our last example, the third one, we want to try it. Okay, you can try it and put your answer in the comment section below, or you can email it to me at learnwithp360@gmail.com. You can also try this example. Let me give you another example. Try it and email it to me. No. Where is work, F is force. density, and v is velocity. Check whether this equation is correct or wrong. Check whether it is actually correct to write this formula or it is wrong. You can use dimensional analysis to do that. Don't forget to like, share, and leave your comment down below.